So we're going to be starting today's lesson on writing and graphing exponential growth and decay functions. So just to review, what does an exponential decay function or growth function look like as far as the function rule or model is concerned? So the general rule for this equation is y equals a times b to the x power. And I like to use the parentheses around that b value just to act as a reminder that when we use order of operations, that we have to make sure we do the exponent calculation before we multiply to that a value. All right, so now to differentiate between exponential decay and growth. So in both situations, they need to have a positive a value, or the a value has to be greater than 0, because that's going to be that initial starting point. So if you were talking about population growth or investments related to money, you'd have to start with something. So you couldn't grow a population based off of a negative value. You can't have a negative population to start. Same thing with money. You can't invest a negative amount of money. Things have to have some value to start with. So in order to do exponential decay and growth, we would have to have an a value that is positive or greater than 0. But then the difference lies with the b value. So the a value is obviously greater than 0, but the b value is going to be different for the two. So when the b value is a very small number, still positive, but very small, between 0 and 1, that is when it's going to be exponential decay. On the other hand, when the b value is greater than 1, then it's going to be exponential growth. So that's where the difference lies. And compound interest is an example of a situation where this would come into play. All right, so the first thing we're going to do is go over how to write the function rule from a set of data here in our table. So the first thing we would want to do is tell whether it is exponential here. Is it growth or decay? And the first thing that we would typically do is look for our 0, and that corresponding value there is going to tell us what our a value is. So in this case, we have an a value of 10. So this would be exponential growth or decay. So then we're going to look for the b value. Now, as long as you have numbers going in your x's that are going in order here, increasing by 1, so we have -2, -1, 0, 1, and 2. If you look at the corresponding y values, you can find some sort of a multiple there. So 2/5 times 5 is 2, 2 times 5 is 10, 10 times 5 is 50, 50 times 5 is 250. So as long as there's a consistent multiple there, the b value in this case is 5. Now remember, if the b is greater than 0 and less than 1, that's decay. As long as my b value is greater than 1, then that's going to be growth. So in this particular example, this is an example of a growth function. So now let's write that function. Y equals the a, which is 10, multiplied by the b value raised to the power of x. So this would be our function rule here for this exponential growth function. So let's take a look at this one. So again, first thing we want to do is look for the a value and the b value, and then we can write that function rule, and we can determine from the b value if it's growth or decay. Now when we look at this one, when we go to find that a value, it's actually -2. Okay, then this here, b value, looks like they're being multiplied by 6. Now on first glance, we might think that this is going to be an exponential growth function because the b value is greater than 1. However, the a value is negative, so it's not exponential growth or decay. So we're actually not going to write the equation for this one because it technically is not exponential growth or decay because the a value is negative. We can't start exponential growth or decay based off of a negative value. You could graph it, but it would be entirely theoretical. All right, so let's look at these examples. Tell whether the table represents an exponential function. If it does, then write the rule. So first thing we're going to look for is that a and that b to make sure that the a value is positive. Then you'll know, okay, I do have an exponential function here. Then you look at the b value to determine is it exponential growth or exponential decay, and then you use both of those to write the function rule. So first thing we're going to do is look for the a value. So in this case, we have an a value of a positive 9. So far we know that this is an exponential function because the a value is positive. Then we're going to look for the b value, which is the multiple that's happening between these y values here. So 1 times what gets me a 3? 3 times what number gets me to 9? And make sure that stays consistent throughout. So we have a b value of 3. Because the b is greater than 1, this tells me this is an exponential growth function. And I'm going to write my rule now. Y equals 9 times 3 to the x power. So number 2. Starting out by finding my a value. My a value here is positive 1, which tells me, yes, this is an exponential growth or decay function potentially. Now I have to look at my common multiple here. Now, if you have some fractions, you don't have to start on the left one and work your way. Just look for the easiest one. So to me, like 1 times 11 is 11, pretty easy. So let me make sure that multiple holds true for all of them. So 11 times 11 is 121. 1 over 11 times 11, the 11s would cancel and I would get 1. And 1 over 121 by 11 would give me that fraction of 111. So this b value of 11 holds true throughout. Again, my b is greater than 1, which tells me this is going to be an exponential growth function. And it's going to look like 1 times 11 raised to x, which of course you don't need to put the 1 in there whenever that a value is 1, it's implied. All right, so let's take a look at the next one. So we have 0 and 1/4. So far that looks good because we have a positive a value of 1/4. So this could be exponential growth or decay. So now I'm going to look for my multiple here. So I typically will like to start on the numbers that are not fractions. 1 times 2 is 2. Is 1/2 times 2 equal to 1? It is 1/4 times 2, it's 2/4, which is 1/2, and 1/8 times 2 would be 2/8, which is 1/4. So this holds true for all. Again, my b value is greater than 1, which tells me this will be a growth function as well. It'll be y equals 1/4 times 2 raised to the x. Okay, so now we're going to go to number 4. Again, I have a positive a value here of 1. So now I'm going to look for that multiple. Well, 25 to 5 is there. I could divide 25 by 5, but we don't want to know what it can be divided by. We want to know what we would be multiplying by. So remember, when you're dividing by something, you're really multiplying by the reciprocal. So in that case, this would be multiplying by 1/5. 5 divided by 5 is 1, so that means 5 times 1/5 is 1. And 1 times 1/5 would be 1/5, and 1/5 times 1/5 would be 1 over 25. So we know 1/5 is the b value here. Now in this case, my b is greater than 0, but less than 1, so this is an example of a decay function. However, we still write the function rule the same way, putting the a value first, the b value here in the parentheses, and raising it to the x power. And then finally, we go to the last one. Now, even if you look at this last one and you see, okay, there's a positive here, so it's possible, right, if I have an a value of 4, that I might be able to write my function here. But then when I look at this pattern here, I notice that there's no number that I can multiply by here. I can add 3 each time, but that tells me this is going to be a linear function, which would graph a line. This would not be exponential growth or decay. Okay, so now let's talk about how we actually would graph this. So again, I prefer to write my equation with the parentheses there. It helps me keep it a little bit more organized versus using the multiplication sign. So step 1 would be to make a table by choosing a few values for x and finding the values for y. Now remember, for all exponential growth and decay functions, the domain is all real numbers. What that means is your domain, you could plug in any value you want for x. Typically, you want to use a 0 and a positive 1 and a negative 1. And then if you want to expand out a little bit, a 2 and a negative 2 will get you a little bit more points to plot on your graph and help make your graph look a little more accurate. So in order to do this, we're basically just plugging in these x values here in for the x, and then we're going to find those y values. So for this first one here, I'm going to do 5 times 3 to the negative 2. Now if you remember our rules with negative exponents, anything that has a negative exponent will go to the opposite side. So this 3 to negative 2 would go to the bottom, and then that would make that 5/9. And of course, you could always do this on a calculator, but I'm going to choose to do it without. Now the next one, we're going to do negative 1. So same idea, we have that negative exponent. So I'm going to move my 3 down to the bottom, and now I'm simply just at 5/3. That's a little bit hard to graph though because it's an improper fraction, so it would be 1 2/3. Okay, now the rest of them are a little more simple because we have 5 times 3 raised to the 0. Now remember, anything raised to the 0 just equals 1. So 5 times 1 is just 5 there. And then when we do 5 times 3 to the first power, well, 3 to the first power just stays 3. So 5 times 3 is 15. And then when we do 5 times 3 to the second power, remember exponent first, that's really 5 times 9, which is 45. So now we want to plot these. So negative 2 and 5/9. So negative 2 is easy to identify on my x-axis, but 5/9 is not there. And this box is going by 5. So that's going to be really, really close to that x-axis. The next one was negative 1 and 1 2/3. So I'm going to go 1 2/3 up, assuming this is 0 to 5 here. So it's a little bit higher. Then my next point was 0, 5. Then my next one was 1 and 15. And then I had 2 and 45. You can see that this graph is really close to the x-axis, and then it starts to go up. And then as it curves, it goes up much more drastically. Okay, so like the directions indicated that the domain was all real numbers. And you can also see that on the graph because the x-axis, which is your domain, spans in both directions with arrows on either side. So that's all real numbers. The range, however, which is your y values, right, is going to be all the y values are greater than 0. Notice they're all above that x-axis, and a way to write this is all positive real numbers. And that's going to be true for all exponential growth functions. Every single exponential growth function that we're doing here is going to have the domain of all real numbers. And if it's in this basic format here where we just have our y equals a times b to the x, it's always going to level out at that x axis. So we will have the range being y is greater than 0. We're all positive real numbers. All right, so let's take a look at this one. Now this example is going to be a decay function. So for this one, this is a decay function. And the reason why it's a decay function is because this is really 1 times 1/10 to the x power. And the b value here is 1/10, which is between 0 and 1. So that would make it a decay function. So again, though, the domain is still all real numbers, meaning we can substitute anything we want in for that x. So just to make things simple, we usually stick with -1, 0, and 1, and then maybe 2 or -2. Just small numbers close to 0 make it a little bit easier to work with. Okay, so if I want to first plug in my -1, that would flip this fraction here, giving me a 10. If I want to raise my 1/10 to 0, that would just make it a 1. If I'm going to raise my 1/10 to 1, that's just going to keep it the same, 1 over 10. And, if I want to raise my 1/10 to 2, I'm going to have to do 1 squared over 10 squared, which would equal 1 over 100. Okay, so again, let's plot these points. So -1 and 10 is going to be right up here. The next one is 0, 1. Then 1 and 1/10, which would be very close to the x-axis, and then 2 and 1/100th, which is even closer. Now this curve, notice it kind of drops down and then curves to start leveling out at the x-axis. So this is an example of an exponential decay curve. And it's always going to go, as you read it left to right, decay is always going to go down and growth is always going to curve up. And here we know that the domain, just like before, is all real numbers because there was no restrictions on what numbers we could substitute in for x. And you can see that the graph goes on, it spans positives and negatives. But the range, however, that's your y values, were all positive. So again, y is greater than 0, or you could say all positive real numbers. It's sloppy there, but okay. Now here we're just looking at the comparison of a few different graphs. Now notice in all 3 of these graphs, they have a b value of 4. But the a value is a little bit different, right? So in this first graph, the a value is 1. In the second graph, the a value is -1/2. In the third graph, the a value is 2. But all of them have a b value of 4. So we know that they're all growth here with a b value of 4. Well, we say they're all growth, but hang on to that thought for just a minute. Okay, so the first one with the a value of 1, that's this graph here. Now we expect growth to curve upward, and that's this one here. Notice the y-intercept was that 1 that we saw, the a value of 1. Now the next one has an a value of -1/2. And notice that this one is technically not growth because look at what the graph does. That negative makes this graph go downward, which doesn't really make sense with a lot of things if you're talking about exponential growth, because you can't have the population going more negative or amount of money that's invested becoming more negative. That doesn't really make sense. So while it's a theoretical graph that can be plotted, it's not exponential growth or decay because it's in the negative realm there. And then you have the third graph, which is very similar to the first one. Okay, so let's talk about how we would classify and write rules for functions based on looking at the actual graph. So if I look at this first example, in example A, I can clearly see that this is exponential decay. And the way I can tell that is because I can look at this graph and I can see that the curve is trending downward or decreasing as I read it from left to right. Now, a couple things. Your A value here is going to be that y-intercept. In this case, that's a 15. Now, if you can tell from the graph that it is exponential decay, then that means that the B value has to be a number between 0 and 1. And if you look at these 2 points here, and for me, it's a little bit easier to kind of think of these as part of a table of values, right? So I have 0, 15, and then I have 1, 5. And you want to make sure you write them in increasing order. So if you had another point, it would be like 2 and something. What is that change? 15 divided by 3. Well, yeah, but we have to write it as a multiple, so it would be 1/3. So then we know that the rule for this would be 15 times 1/3 raised to x, and that's this equation that you see here. So that's where that comes from. Now, if we take a look at the next example, this one is trending upward as we go left to right. So this one would be exponential growth. Now here, my A value again is that y-intercept, so it's just going to be a 4. And my B value is that change from 4 to 8. So how do I get from 4 to 8? Multiply by 2. And so then I would write my function rule, which would be 4 times 2 to the x power. And that's the equation that you see written here. All right, and that concludes our lesson on graphing and writing the function rules for exponential growth and decay functions.